So, good morning, everyone. I am PhD candidate Nicola Capodieci, and I'm here to present my ongoing work of my PhD research, which is entitled Self-Expression in Ensembles of Autonomic Components. My supervisor is Professor Giacomo Capri. So, we are in the field of ensembles of autonomic components. An ensemble is a potentially large set of components, and with components is an extremely generic term in which we define any entity that can deploy a certain degree of autonomicity. So when designing these kind of systems, so these collective and adaptive systems, we can think of them as they should be able to deploy the so-called self-star properties. So we have to think about components and ensembles as a whole, able to self-heal, self-repair, self-organize, and so on. So to autonomously recover from both hardware and software faults. That's how they should reach self-adaptivity, which is the property of sustaining themselves in open and non-deterministic environments. So to keep going their task, obtaining their results, optimization, and no matter what, because we are thinking about having these ensembles inserted in a changing environment. On the top of these properties, the element of novelty is to think about the existence of another self-star property, which we define as self-expression, which we define as the ability of an ensemble to change their coordination pattern during runtime execution of tasks of variable complexity. In other words, let's suppose to have a computational problem that we want our ensemble to solve. We can think about many ways to solve this problem, and each of these ways is a different collaborative effort among ensemble. And we can think that each way for solving this problem can result in different outcomes, and sometimes when the ensemble is inserted in a dynamic environment, it can be useful for the ensemble to decide to switch from one coordination pattern to another. The big challenge here is how we design these kind of systems in terms of methodologies, frameworks, and blueprints. And several approaches have been investigated in literature, and we are focusing on two completely different point of views. One point of view that is coming from traditional autonomic computing, software maintenance cycles, and another completely different point of view, which is bio-inspired approaches, in particular regarding my PhD research on artificial immune systems. And what we want to obtain by trying to solve this design problem with two different perspectives is that we believe there are commonalities, differences, and therefore we can think about a unified framework in which we can use to exploit the advantages of both these point of views. Now, to be more specific, on the point of view of the autonomic components, I was obviously referring to the well-known IBM's MAPEK feedback loop for modeling autonomic components. On the other hand of the artificial immune system side, we have cognitive networks, as firstly theorized by Jeroen Cohen, which is a very famous immunologist. Well, the point is that, unfortunately, I don't have much time to go deep in these methodologies, but there are indeed similarities, and there are indeed differences. And I think that those kind of point of views are complementary when we want to design these kind of ensembles. And to make it short, I can say that both these methodologies rely on the fact to have a matching condition between the external environment, and then the ensemble has to match the external condition to a proper action or set of actions. Therefore, we have then a feedback loop for trying to provide a feedback to the system in order to keep doing the same actions or change to other strategies. Obviously, there are some drawbacks in the sense that we assume that we have a known logic between action and condition, and sometimes it's not always like that. Sometimes the systems are so complex that are really difficult to study, and therefore we don't know this logic a priori. Or else, what can happen is that the single components of the ensemble are not aware enough of their surroundings to draw these kind of conclusions. Therefore, as a very preliminary study as of now, we are also investigating another point of view that has its roots in probability theory. Now, let's go back to autonomic computing and artificial immune system. I think it would be very interesting to see how we can apply these methodologies to a case studies as a proof of concept. So let's take a simple foraging task in swarm robotics. Let's suppose we have a delimited space called arena, in which our robots are inserted in. This arena has two distinctive areas, a food area and a nest area. Each robot has to travel to the food area, pick up a food unit, and go back to the nest area. And obviously, this task is iterated over time. The point is that our robots do not have any cognition of space and absolute orientation. So their collaborative efforts, their coordination pattern should be aimed to help themselves out to find one point to the other of these arenas. And these arenas can have different complexities in terms of size and obstacles. So we thought about 3 different coordination patterns for solving this kind of problem. And when we design our artificial immune system net for helping them select the fittest coordination pattern. Going deep in our architecture, we can think about each robot as a lymphocyte, virtual lymphocyte, which has a collection of virtual antibodies that are interconnected among each other through a net of stimulation and suppression signals. That's how a virtual antibody looks like. We have a condition receptor, which is actually bound to the external condition that we are monitoring. On the other hand, we have another receptor, which is based on utilities, so the quality in which we want the task to be completed. So if we have, in this specific case, a task in swarm robotics, we can think about minimizing the energy consumption, minimizing the number of sensor and actuator used, or maximizing, for instance, the total amount of food unit over the single time interval in which we are measuring this. Then we have the central part, which is the action. So the correspondent action can be that we want to match with the perceived external condition in order to obtain those results. And what you can see here is strings that are actually not single actions, but they are referring to coordination patterns. So set of actions, so collaborative efforts. We have a baseline algorithm for trying to solve this foraging problem. We have a purely swarm approach, which is represented by a robotic ontology optimization version of the very well-known family of algorithms in which each robot can act himself as a pheromone. And then we have a purely peer-to-peer approach in which the robots actually rely on real communication using infrared signaling and fixed protocols of communication. Now, another step out of our architecture is, okay, let's see what happens when we have more than one robot. So in each robot, we have this net of antibodies. Thanks to the network of stimulation and suppression stimuli, we can easily calculate a concentration for each of these antibodies. So basically, we are in the field of idiotopic networks, so the first model proposed by Bersini. And it was firstly applied in a single robot by Ishiguro et al. In the middle of the 90s. So the elemental novelty here is basically try to extend this methodology to distributed architecture, so more robots and not selecting a single action, but selecting a collaborative effort. And so what happens is that time interval after time interval, the concentration of each of those virtual antibodies explain us the history of the past experience of the single robot. So what the robot has to do is to share their concentration values as sharing their own experience to at least nearby robots. Communication is done through infrared signaling, and we are basically simulating all of this. So the point is, the robot at a certain point has to select the antibody which bounds to the fittest coordination pattern in order to optimize the performance in this specific task. Evaluating this kind of approach is not very easy, because it's what we should do is basically compare this to other methodologies by other people with the same simulation framework in the same condition and everything. So it's very difficult to try to provide a definitive answer. What we can do is that, okay, we have our methodology. What we can do is try to solve this problem with our methodology and compare it to solving the same problem with the same condition by not changing the coordination pattern. So we have fairly robust algorithms, have coordination pattern. We can use them to compare with our methodology. So we can evaluate it through different point of views. We can take a very long experiment and see at the end of experiment how many food units the ensemble managed to bring back. And on the other point of view, is saying to let's take time interval after time interval to see how many food units have been brought home just in that little short time to see if there are some variation over time, basically. And what we can say is that our methodology performs best if the arena is complex, if we have a very big arena, if we have a lot of obstacles. If the arena is not that complex, our algorithm is not always the best performing one. However, it shows improvements over time. The amount of food collected over a unit is constantly improving over time, and this does not happen with taking a single coordination pattern alone without changing it over time. So what we have here, in my opinion, is some kind of adaptation, or at least it's learning how to improve its performance over time. And sometimes at the end of the experiment, it managed to be the best, sometimes not. But it's still, I think, a very good result, at least at this point of my research. So to conclude, I must say that we can also draw interesting discussion about this adaptivity is obtained in terms of what happens is that not always the ensemble reaches a globally shared decision on which coordination pattern to use together. What happens most of the time is that we have the swarm to create clusters. So half of the swarm, for instance, is following a coordination pattern, the other one is following another one, but somehow they manage to bring good results. As for future work, I will probably try to apply the same methodology to other case studies, not necessarily in robotics, or what we can do is to improve this scenario by try to what is known in artificial immune system literature and somatic hypermutation, which can be written as parameter tuning of the inner parameter of the coordination pattern themselves. If you want to know more, most of these topics have been covered in some publications, conference proceedings mainly, and that would be all. Thank you very much for your kind attention.
Thanks for your talk. So one of the next applications is about the smart grid.
Yes, actually, in the first in the first day, I was trying to apply the concept of self-expression in the smart grids. And so basically this year I had to choose, and I basically focused on swarm robotic. But yeah, there are applications in, as I said before, it's autonomic components have to be seen as something very generic. It can be robots, there can be agents, so we can use these agents in the smart grid. It's a very common application, especially in negotiation. And so yes, we can.
No, all this makes me think about game theory, because I mean, it's like having a set of players with these robots, which play according a sort of distributed strategy.
Yeah, exactly. And actually it was the topic of my master thesis. So having again theoretical algorithm for helping software agent inserting the smart grid with their negotiation, basically. So yes, it's a well-known topic in game theory. Thank you.
So thanks again.